Good morning, everyone. Welcome to another session of AESP 420, Flight and Orbital Mechanics. Today we are going to start with gliding performance and then move on to range and endurance. Maybe even smaller. Okay. And then we'll talk about other topics afterwards if we had enough time. So gliding performance, if an airplane is in glide, it effectively means that there is no thrust. The only forces that are going to be available, if this is your flight path, and this is your horizon, you will have your theta like this, and your lift is of course perpendicular to your flight path. Drag is tangential to the flight path. Your weight is perpendicular to the horizon. We're going to have the same theta here. So equations of motions for a gliding flight will be d equals to w sine of theta, L equals to w cosine of theta. There are a couple of things here that we can calculate. First one is the lift to drag ratio. So if you divide these two equations, you're going to get sine of theta divided by cosine of theta, which is tangent of theta, is going to be equal to d divided by L, or 1 divided by L over D. Okay? And the smallest equilibrium glide angle, which is essentially going to give you the maximum range. So the minimum glide angle, minimum theta here, can be found when your L over D is maximum. So tangent of theta mean, the smallest equilibrium glide angle, and by equilibrium, we are talking about the fact that we want to maintain the unaccelerated flight. Is going to be 1 over L by D max. Okay, the next thing you always want to calculate when it comes to gliding flight is going to be the range of your gliding flight. Okay, let's say this is where your airplane is located at time 0, and this is the altitude. You want to find how much it will go with a constant lift and drag and all of those forces. With a specific theta, flight path angle. Of course, here, based on the three calculations, you can see R is equals to H divided by tangent of theta, which means that R is equals to H divided by multiplied by lift to drag ratio. This also means that to get the maximum range, you have to maximize the lift to drag ratio. This was a topic that we had to cover in the previous lecture, but we couldn't finish it. So I had to come back to it and finish the discussion over there. But the next thing we want to talk about is the range and endurance. Range and endurance will be calculated differently for a propeller-based engine and for a jet engine. So we have different approaches here. We'll talk about these different approaches in a bit. Okay, the first thing you need to understand is that how do we define range and endurance for each of this engine. Essentially, with each of these engine types of engine, endurance is how much your aircraft will fly, how long your aircraft can fly on a full tank of gas. Okay, you want to find a time basically. Range can be defined as the total distance traveled by your aircraft on a full tank of gas. Okay. But why is the perspective different when it comes to two different engines here? The main reason goes back to power and thrust. When we are dealing with a propeller engine aircraft, your power is the determining factor, is the goal. Power calculations and power analysis. But when it comes to jet engines, thrust is the main point of the jet engine analysis, as you will see later in your energy and propulsion course. So let's just start with the propeller and power-based analysis. So propeller-driven airplane. Before finding range and endurance, we need to define a new parameter that is very common called SFC. This stands for a specific fuel consumption. Okay. It can be calculated by pounds of fuel per your power multiplied by time. So this is essentially weight of the fuel consumed per unit power per unit time. Weight of the fuel consumed, we are dividing it by power and time, which means that we're going to get the weight of the unit consumed per unit power per unit time. So if you do the analysis, and you can definitely do it yourself, and we're going to see that later on, is that for a propeller-based engine, max endurance is going to occur when the airplane is flying at minimum power required. Let's call it PR of min. Hopefully you remember what power required was. And if you go back to your notes, you're going to see that the minimum power required itself is going to happen when this ratio is maximum. CL to the power 3 by 2 divided by CD is maximum. That would give you the minimum power required. Okay? But how can we find this minimum power required? The first thing is you need to define your weight. Let's call it your aircraft total weight at time 1 is your aircraft initial weight minus the weight of the fuel. Okay? And then we can define the changes of aircraft fuel weight, which is going to be equal to the changes in aircraft weight in general, because that's the only thing that is going to change in the aircraft, hopefully. You are not dropping anything down. And that is based on this definition of SFC, is going to be equal to your SFC, negative SFC, we are losing weight, multiplied by power, multiplied by the time, your time dt here. Okay, and for simplicity, your book is using C instead of SFC. So if you were to read the book or for the continuation of this discussion, we are going to do the same thing. So let's rearrange this to get to dt equals to negative dw divided by CP. C is your SFC, specific fuel consumption. And of course, if we take the integral here from 0 to the time where your fuel tank is empty, right? That's the time where you get your endurance of the plane. We will have the answer. We will have the endurance. And over that time, your weight is changing from the initial weight W naught to the W1, which is the weight of the aircraft, the structural weight of the aircraft, essentially. Okay. The integral on the left-hand side is going to be giving you e minus 0, so just e. If you bring the negative sign into the integral, you're going to get the integral of W1 to W0 dW divided by Cp. So that will be your equation for endurance. But how can we find the range? Pretty simple. Just multiply this equation here, this equation, with a the rearrangement of this equation where we have dt, this one, with a v infinity before taking the integral. So we're going to get v infinity dt equals to negative v infinity dw divided by cp. Okay, and we already know that v infinity dt is equals to ds. Okay, because v infinity itself is ds divided by dt, so we can get the ds based on that. So ds is going to be equal to v infinity dw divided by cp. So you take the integral from 0 to r this time, and this for this one is going to stay the same. And your r is going to be the integral of w1 to W naught, V infinity, dWCP. The only thing we really need to know here to be able to calculate these two integrals for endurance, this is endurance, for a propeller-based engine, and this is range for a propeller-based engine. The only thing we really need to understand here or need to have here is the rate of change of W, the rate of your fuel burning, essentially, if you will. And we usually, right, at this point, we don't know it. But there is a guy called Birgit who further, and these were all very general formulas. We didn't make any assumptions here, right? Just based on the definitions. Okay. But this guy further developed these formulas to get the formulas for a level unaccelerated flights, which is the flight we are mostly focused on. This is the type of flight we're mostly focused on. So for a level unaccelerated flight, you can find your power as power available divided by eta, that's the mechanical efficiency. If you recall, we define PA as eta in mechanical efficiency multiplied by the power that is produced by the engine. Right? And from the analysis we have had before, we know that power available is equal to drag multiplied by V infinity. Divided by eta. So you plug that in the range equation, you're gonna get range is equals to integral of W1 to W naught, V infinity dWCP. This is the equation we already had. And then W1 to W naught, V infinity, just replace the equation over there, dW divided by CD V infinity. Okay, V infinities will cancel out. And we eventually gonna get R is equals to W naught, V infinity V infinities will cancel. Eta dWCD. Right. Let's multiply this whole thing by a W divided by W. Okay. For a level unaccelerated flight, we know that W is equals to weight, so we're going to replace one of them with L is equals to lift. So we're gonna replace that with L, and eventually your range equation is going to become eta L dW divided by CDW. Okay, we can replace this L divided by D by CL divided by CD, which is not going to change in a level unaccelerated flight, so we can take it out of the integral. Take all of them, actually. C and eta are not going to change as well. So we're going to get eta divided by C multiplied by CL divided by CD integral of W1 to W naught dW divided by W. Okay. So we already know that what is the solution to this integral. Your range is going to be equal to eta divided by C, CL, CD, natural log of W naught divided by W1. Okay, how can we maximize this range? Of course, if you increase your efficiency, you're going to maximize your range. If you decrease your specific fuel consumption, so the fuel that is being consumed per pound of fuel per time, per power per time, per unit power per time, you're going to get a higher range. But the other point here is that if you maximize your CL by CD, you're going to get your maximum, your lift to drag ratio, you're going to get your maximum range, right? So Rmax is going to happen when your CDCL is max. That's true for a propeller based engine. Okay. We can do the same analysis for endurance. W1 to W0, dW divided by Cp. This was the equation for endurance. Then you replace dV infinity for P, eta dV infinity. We're going to get dW dV infinity, right? Multiplied by W divided by W. Replace one of the W's with lift. And eventually, what you're going to get for endurance is going to be a little different, right? Because you cannot remove this V infinity. This is, I'm sorry, this is capital dV infinity. We cannot remove this dV infinity here. It won't go away, right? So you're going to end up with a W1 to W0, eta divided by C, L divided by D. We can replace that by CL, CD, and dW divided by V infinity. What can we do for this V infinity? We already know that L is equals to weight is equals to 1/2 rho infinity V infinity squared SCL. So we can replace that. We can rearrange this equation to get to V infinity is equals to square root of 2W rho infinity SCL. This is an equation we have already seen many times. You can replace that in the equation. You can plug that in the equation, that we have. Right? But you first have to multiply by W divided by W, replace one of them, and we have already done all of these, right? And there should be a W here. Okay. So if you do so, you will end up with this equation. W1 to W0, eta divided by C, CL, CD, integral of rho infinity, SCL by 2, dW W3 by 2. Yeah, this is what you're gonna. And we can take the integral very easily here. We can just multiply, bring the CL out of the square root and multiply it by CL here. You're gonna end up with CL 3 by 2. You can take that out of the integral and then only take the integral of dW divided by W3 by 2 to raise to the 3 by 2. Eventually, your endurance is going to be -2 eta divided by C CL to the power 3 by 2 divided by CD, rho infinity S divided by 2 multiplied by 1/2, then W to the power 1/2, -1/2. That changes from W1 to W0. Plug the values in. You will end up with this following eventual equation. Eta divided by C, CL squared, CL raised to the power 3 by 2 divided by CD multiplied by 2 rho infinity S W1 minus W0. Okay. This will be your endurance for a propeller-based engine. How can we maximize this propeller-based engine's endurance? Of course, we can do a lot of analysis. We can play a lot with W, we can play a lot with eta and C, but eventually, if you are flying the plane, you cannot play with any of these, right? But these are going to be structural constraints. But you can play with the maximizing CL to the power 3 by 2 divided by CD. So you're going to get the maximum endurance where CL 3 by 2 divided by CD is max. Okay, let's do the same analysis for a jet airplane. As I said, jet-based airplanes, jet engines, are usually characterized by the thrust produced compared to the propeller engines, who are usually characterized by the power produced. We can actually use these formulas for both of them, right? Because the only difference here, for one we are using power, for the other one we are using thrust. So if you know the power for the a jet engine, you can definitely use the power-based equations we have found, but you have to know power and the specific fuel consumption for that jet engine, which are not available. For a jet engine, we have a thrust, a specific fuel consumption, okay, which is defined as pound of fuel divided by pound of thrust by time. Okay, thrust specific fuel consumption. So we're going to use, and since we don't have the values of SFC for jet engines available, we essentially we are forced to do the thrust-based analysis, because we're only going to have the thrust specific, in most cases, thrust specific fuel consumption available to us, right? And if you do the analysis, you are eventually going to get to the same results. The only difference is going to be this, right? So we have defined, let me actually do, we have defined the thrust specific fuel analysis in a way that the changes in weight, okay, changes in pound of fuel here, is going to be equal to your thrust specific fuel analysis multiplied by whatever we have here. So let's use C of T for thrust specific fuel analysis, thrust available multiplied by dt. Okay, look at this equation here and then compare it to the equation we had for the power based, propeller based, right? The reason we didn't do power available here is because of the mechanical efficiency. Okay, but it's essentially the same equation. The only difference is the specific fuel consumption is replaced by the thrust specific fuel consumption, and power available is replaced by thrust available. Okay, so the general form of equation for your endurance, you're gonna get negative W naught to W1 dW divided by CTTA. And we already know that thrust available is equal to thrust required for an unaccelerated flight. The Breguet equations apply here. Unaccelerated level flight is equal to drag, and lift is equal to weight, right? Multiply this by W divided by W, replace this W by lift, replace thrust by drag, you will end up with the equation like this: 1 divided by CT, L divided by W, dW divided by W. You can take the integral simply, and your endurance is going to be equal to 1 divided by CT. As you can see, we don't have the mechanical efficiency here. CLCD, natural log of W1 to W1 for endurance. Okay. So to maximize your endurance, you have to maximize CL divided by CD. Compared it to the previous case, for endurance, we have to maximize for a propeller-based engine. We have to maximize, or for a power-based analysis, we have to maximize the CL to the third 3/2 divided by CD. Here we have to maximize lift to drag ratio to get the maximum endurance for a jet engine. So CL max is going to lead to endurance max. Let's do the analysis for the range. You have to come up with ds, which is V infinity dt. So we have to add a V infinity in our analysis. All right. Negative W naught W1 V infinity dW divided by CT TA thrust available. We can multiply this by W by W, replace thrust with drag on accelerated level flight, and we are going to end up with this integral, V infinity V naught, W1 W naught, V infinity CT, CL divided by CT, CD, dW divided by W. Okay. We have to somehow bring in the CD and CL for the V infinity, and you already know what to do here. V infinity is the square root of 2W divided by rho infinity CL S, right? That was the idea. So when you plug that in here, this is what we are going to get. For the endurance case in the previous discussion, we had the infinity in the denominator, but now we have the infinity in the numerator. So square root of 2W divided by rho infinity CLS, CLCD. We are going to get CL1 half here. And then dW divided by W. This will be W to the power 1/2, and this will cancel out. If you do the analysis, if you take the integral, you are going to end up with this equation for range. Two square root of 2 divided by rho infinity S, 1 over CT, CL squared, CD, W naught minus W1 to the power 1/2. So how can we maximize the range? For a jet engine, we have to maximize CL to the power 1/2 divided by CD to get the maximum range. Okay, so you already see that the presence of CL to the power 1/2 divided by CD, also CL divided by CD, lift to drag ratio, CL to the power 3/2 divided by CD, and we have another CL divided by CD, okay? We already know the relationships for CL to the power 3/2 by CD. We already know when that becomes maximum. We already know when it becomes maximum for CL divided by CD. We did the analysis when it came to the available power required, and also available thrust required discussion. But we don't know how to get the maximum CL to the half to CD, right? How to get the maximum of this. So I'm going to give you all of the equations. I'm going to do a review of the previous equations that we have gone over. and then I'm gonna give you the equation for the last one. So to get the CL CD max, if you recall, your CD, your parasitic drag had to be equal to your induced drag. And then we could have found CL CD max as CD naught pi EAR to the power 1/2 divided by 2 CD naught parasitic drag, okay? For CL to the 3/2 divided by CD max, your CD naught had to be equal to 1/3 of the induced drag, okay? So 3 CD naught, then for the maximum equation, let me CL 3/2 divided by CD max is going to be equal to 3 CD naught pi EAR 3 to the 4 divided by 4 CD naught. And then eventually the last one is to get CL divided by CD max. To get this to the maximum value, what we need to have CD naught equals to 3 CDI induced drag. Which essentially is going to mean that CL to the power 1/2 divided by CD maximum is going to be equal to 1/3 CD naught pi EAR to the power 1/4 divided by 4/3, and all of this 1/3 is also inside the parentheses. 4/3 CD naught. Okay, there is a bonus point here for you guys. Prove these relationships. And for each proof, you are going to get 1 bonus point. So if you submit all 3, you're going to get 1.5% of your final grade, right? And it is pretty easy to do. You essentially, in your parasitic drag calculation, if you recall, your total drag was equals to your parasitic drag plus CDI, right? And this is your total drag, this is your CL. So your CD is CD naught plus CDI, right? And if they have to be equal, here you're gonna get 2 CDIs, right? How did we calculate CDI? CDI was your CL squared, right, divided by pi EAR, right? So you just plug that in this, like this condition and this, and then you should get to this final equation, right? The same is true if you apply this condition and this here, you should get to this final equation, and same is true for all of these. Okay. So if you submit this bonus point, you're going to get a lot of credit for it, so make sure you do so. Okay. The next thing we want to discuss is the takeoff performance. Takeoff and landing performance. So takeoff and landing performance is going to be different with all of the discussion we have had so far. Takeoff and landing performance, also landing. The main difference here is that your velocity is either going from 0 to landing or liftoff velocity, or your velocity, landing velocity, goes from this to 0. What does this mean? This essentially means that the unaccelerated flight assumption is not true anymore. We have acceleration. Okay. We are still going to assume that your force remains a constant value, but we definitely are going to have acceleration. So this is if this is your plane at body 0, at time 0, your velocity is also 0. At the liftoff condition, we are going to have f constant, a velocity, right? And the velocity 0, velocity 0 to velocity v. I'm going to calculate this distance essentially in the takeoff performance. This distance. How can we calculate this distance? The first thing you need to keep in mind is that the liftoff velocity is something we define, right? And liftoff velocity, in theory, can be equal to your stall velocity, right? This essentially means that you are generating enough lift to counter the weight force, in theory. But we are not going to use the stall velocity. We're going to be safe. We are going to be a little ahead of a little higher, go a little higher than the stall velocity. So let's write the equations of motions for this. This time we cannot say sigma f is equals to 0. It is always equals to ma, because this is an accelerated flight. Then a can be replaced with dv dt. Right? If you rearrange this equation, your dv is going to be equal to f divided by m dt, right? And we're going to assume that your velocity changes linearly, so constant acceleration, which essentially means that we can take the integral here, and your liftoff velocity, since we started from 0, or your velocity if you start from 0 in general, is going to be equals to v equals to f divided by m multiplied by t. And if you rearrange this, your t is going to be equals to vm divided by. So your velocity at any point here can be calculated based on the time you have and the amount of force and also the mass. But what about this liftoff distance? Your ds, liftoff distance, is going to be equal to v dt, which is equals to f divided by mt for v multiplied by dt. Take the integral from both sides, from 0 to s, from 0 to t. You're going to end up with the distance equals to f divided by m t squared divided by 2. We can also bring the velocity from the previous equations in here and relate the distance to the velocity at any point multiplied by m divided by 2f. Okay. But what are the forces that are involved in here? Okay. Let's say this is your x and y. This is your plane that is going in this direction, which essentially, since we always assume the plane is not moving and air around it is the thing that is moving, so we're going to have v infinity. In this direction, your weight is going to be applied to the center of gravity. We're going to have lift, we're going to have drag, and then since you are rolling on the ground, we are going to have the ground force, R, right, in the direction of drag. So your F in the X direction is going to be equal to your thrust. We also have the thrust that is pushing there. I forgot about this. Your thrust minus your drag minus your R. If you recall from your physics, your R is going to be your friction coefficient, mu of R, multiplied by the forces in the normal direction, which is weight minus lift, right? So we essentially have all of the forces that we can have, and this thing is Newton's law, Newton's second law is equal to md v dt. Okay, lift here, just a reminder, is equals to 1/2 rho infinity v infinity squared SCL, and d here is 1/2 rho v infinity squared S CD, which is CD naught, plus CL squared divided by pi EAR. But here, we are going to multiply your induced drag by something called a ground effect. Why do we do this? It essentially goes back to the philosophy, the idea behind the induced drag. The idea was you're going to get some wing tip vortices that higher pressure area is going to, wing tip effect, is going to go to the top of the plane. Okay, that was the idea of it. If this is happening, which this always happens, you are going to get the induced drag. And the induced drag coefficient can be calculated using this equation, right? You're going to lose some lift to drag. But what happens when you are moving on the ground is that you are going to limit this pressure movement. Right? Let's say this is your ground, right? You won't have any flow that is moving from here to here because this is going to hit the ground, right? And stay underneath. So you won't lose as much pressure. That's the idea. Okay, so we won't lose as much pressure, which essentially means that we have to multiply this by a correction factor. This correction factor phi is called the ground effect. This essentially means that your total drag is going to be lower on the ground, right? Your total induced drag is going to be lower, which is, if you keep the parasitic drag constant, your total drag is going to be lower. But how can we calculate? Of course, this value of phi is always smaller than 1 or equal to 1, right? When you are already flying, your phi is going to be smaller than 1, equals to 1, right? How can we calculate this phi? We have an equation that is given by a person called McCormack, right? This is an approximation, essentially. This is a correlation. Okay, so McCormack, right? We can calculate this phi as 16h multiplied by h. This is your altitude h, or how high, height of the wing, right? Just the wing, right? From the ground, divided by your wingspan squared over 1 plus 16h divided by b squared. This is how you can calculate your phi. Okay. So we know how to calculate lifts, we know how to calculate drag, and we should know how to calculate forces, right? No. Why is that the case? Why can't we calculate the forces, total forces that are going to apply from 0 to liftoff? Your force is going to be a function of velocity, right? And your velocity is changing from 0 to v infinity. So what should we do? In the equation, we are going to use an effective force, which is essentially T minus thrust is not going to change. The only forces that are going to change are drag and lift, right? We are going to use an average value for this. So average drag, average lift constant. But to get the average value, you first have to have all of the values or distributions from 0 to v infinity or v liftoff, right? How can we remedy that? Essentially, what we are going to do, instead of using the average value, we are going to use the value we're going to get, which can be shown that this is a very good approximation. For the average value, we are going to use the value of lift and drag when V is 70% of your liftoff force. So all of this can be replaced by 70% of V liftoff. Okay. Whatever you set your V liftoff to be, you calculate the 70% of it, right? To make it easier for you. So we have lift rho infinity, 1/2 rho V infinity V infinity squared CL, right? S. You have your S, that's your wing area, span area, right? Your V infinity is going to be 0.7 V liftoff. V liftoff, this is something you determine by design. We have the density, and we are going to assume the density is going to remain constant. So rho V infinity, plug the value for velocity in, you should be able to calculate lift. Pretty simple, right? And then you do the same thing for drag. Mu r is your ground property. If you are on a paved ground, if you are on asphalt, if you are on whatever, your ground property is going to change, and this is the value you are going to be given, or you can read from tables. Okay, just plug that in, and you should be good to go. Okay, so we have the effective force now, and we also know how to calculate S, right? This was S. We're only going to replace F here, and we're going to change VL, V with V liftoff here, and M is W divided by G. So let's substitute all of those values in. Your liftoff distance is going to be V liftoff squared WG, W divided by G, divided by 2 T minus D plus mu R multiplied by V minus L, average value. Okay, this will be your final equation that can help you calculate the liftoff distance. But how can we find V liftoff? I said in theory, your V liftoff is your V stall, right? When you get to V stall, you should be able to fly. But since we want to keep it safe in our design, we use 1.2 times of the V stall. And we already know how to calculate V stall. You're going to get the VSL, then your CL is the maximum. So 2W rho infinity S CL max, right? This is an equation we have seen many, many times. So that's it. You can replace this equation. You can plug that in this equation, and you're going to get your liftoff only as a function of your forces and the structural parameters. 1.2 to the power 2 is 1.44. W squared divided by G rho infinity S CL max T minus D plus mu R W minus L, and this whole thing, this part is the average part, or 0.7 VLO, so that doesn't really matter. Okay, this will be our final equation. Based, if you have the forces at 0.7 liftoff velocity, you have the drag, you have the lift, you should have the weight, you should have the thrust, you should have the maximum CL, you should be able to calculate the liftoff distance you need. Liftoff distance is essentially going to be the distance you have to fly to go from zero velocity to liftoff velocity. And then you will be able to fly. If you go further than this, your velocity is going to be increasing even further, and your airplane is going to be pushed up without even you changing the stick location, without even you pulling the stick yourself to increase the camber, right? If you're in a real flight condition. But as soon as you get to the liftoff, you should be able to do the analysis. You should be able to lift off, essentially. Okay. Let's have a small discussion about how V liftoff is related to density. As you can see from this equation, we have a rho infinity here, and rho infinity also appears in the lift and drag as well. So essentially, your liftoff distance is a function of, is related to 1 divided by rho infinity squared. So for higher density, you're going to need lower liftoff distance. So essentially, when you are in the summer and you want to get off, you are going to need a higher liftoff distance. So summer days, or let's say hotter days, where density is smaller, or higher altitudes, both of them. So if you're, for example, in Peru, which is I think is the highest country in the world, you are going to need a bigger tarmac, a longer tarmac. That's the idea. And we can do one simplification before moving forward. For liftoff distance, we can just assume the thrust is going to be so big that it's going to eat all of these drag and the friction force and all of those things. We can just simplify your equation to be 1.44 W squared G rho infinity S CL max and T. Okay. So next step is to talk about the landing performance. Landing performance is essentially the same thing as the liftoff performance. The only difference here is that you are dealing with the velocity going from V infinity or V landing, let's call it V landing, to 0. And you can hit the ground when in theory, you can hit the ground when your landing velocity is equals to stall velocity. So you have already decreased your velocity low enough. Okay, that will be the best condition. That will give you the lowest landing distance. Okay, but what are the forces that are present here? Of course, your thrust is going to be 0, right? In theory, again. So the only forces that are here is going to be drag and the ground force, which is equals to m dv dt, right? Your second law. You can do the exact same analysis. The only difference is that your acceleration is negative. you're reducing your velocity, so your ground distance is going to be equal to F divided by M, negative F divided by M, T squared by 2. You can definitely get here on your own, definitely, and your SL eventually is going to be your touchdown velocity. That's the velocity where you touch the ground, right? Divided by Vg, 2 V plus mu R, V minus L. Again, the average value, that will be the 70% of your touchdown velocity this time. And your touchdown velocity is something that you design to remain safe. We are going to say it is 1.3 stall. The reason we have a higher value here is that as you move further away from the stall, your airplane is going to be more stable, more controllable, essentially. And for landing, you're going to need much more control compared to liftoff, right? So just to be safe, 1.3 instead of 1.2. 1.3 square root of 2W rho infinity SCL max. Okay, this will be your touchdown velocity. You plug that in. Your landing distance, where you go from VT to zero velocity, is equals to 1.69 W squared divided by G rho infinity S CL max D plus mu R W minus L, which we have to evaluate at 0.7 V touch. This will be your final liftoff velocity, okay? In the more modern aircraft, what we have is the reverse thrust. In the more modern engines, reverse thrust. So if you have the reverse thrust, essentially your thrust is going to act in the same direction as drag. Is going to come and help the drag. So your forces are going to be negative TR, negative D, that's the reverse thrust, minus drag, mu R, W minus L equals to M dV dt. Eventually, you're going to get the same calculation. The only difference would be you are in the denominator, you are going to get the value of thrust. CL max TR plus D plus mu R W minus L 0.7 VT. Okay, and then yeah, this will be your equation. So we understand how to calculate the landing distance based on a touchdown velocity and how to calculate the liftoff distance based on a touchdown velocity. We are essentially at the end of the flight mechanics part of the chapter, part of the class. There are a couple of things that we need to cover that we will cover on Tuesday, the upcoming Tuesday, and then we will talk about the exam a little bit. I will also post a homework sometimes today, but I don't know. I can, please reach out to me. Please send me an email. We will also talk about this on Tuesday. What I'm going to do is that I'm going to put the due date on Wednesday instead of Thursday, right? And if I do that, you essentially have to submit your work by Tuesday to get the solutions on Wednesday, right? So you have the solutions for your homework solutions by Tuesday. I will make sure to grade your homeworks as soon as possible before your exam one. So going out of the exam one, you will have a good idea on what your grade is going to be at this point of the class. Okay, but the only things that remain here We need to talk about the turning performance. That's another type of accelerated flight. Very simple turning performance though. And then we are going to talk about the accelerated rate of climb. We're going to use the energy method for it. And that will be it. That will be all of the discussion we're going to have for the flight mechanics. And then we'll move on to orbital mechanics from after exam one. I hope you have a good weekend, and I'm going to see you all on Tuesday.